Have you ever, like, stumbled on something that seems, deceptively simple at first glance, but then when you really start to dig in, you realize there's this whole universe of complexity hidden beneath the surface?
It's like finding a hidden door in a seemingly ordinary house,
Mm,
right?
mm.
And you open it, and behind it, a sprawling labyrinth full of twists and turns and unexpected connections.
Okay, I'm intrigued. So tell me more. How does it all work? What makes these, what are they called again?
Nestedly recursive
Right,
functions.
those. What makes them so special?
So imagine a set of instructions, but the catch is that these instructions, they refer back to themselves. That's the essence of recursion, right? Now picture those instructions, not just referring back to themselves, but nested within themselves, like a set of those Russian dolls where you open one and there's a smaller version of the same doll inside.
Okay, I think I'm starting to get the picture. But can we ground this with an example? I know our the stuff we've been looking at talks about this function. It's called P312, right?
P312, yeah, it's a prime example of how you get this like unexpected complexity can emerge from these really simple rules.
So walk me through it. What is P312 all about?
Basically, it's defined, well, it looks like this. Fn a play 3 plus fn fn2. So the main thing here is that the function, this f, it's defined in terms of itself.
Okay, so that's the recursive part.
Exactly. And then, because we're applying f to the result of another f,
That's where the nested comes in.
you got it.
It's like a mathematical snake eating its own tail, right?
Uh-huh, kind of.
But instead of like disappearing or something, it creates something totally new.
Yeah, and that's the thing. The results, they're anything but, like, predictable, you know?
Really? So tell me, what happens? Like, if you actually try to calculate this P312 thing, what do you get?
Well, if you start calculating the values of P312 and you just keep plugging in bigger and bigger numbers for n, you might expect to just get, like, a jumbled mess of
Like,
numbers.
that's what I would think. Just pure chaos.
But here's the really surprising part. There's actually this, like, hidden order within what looks like, chaos, this, like, beautiful underlying order.
Wait, are you serious? You're telling me there are patterns in this seemingly random sequence of numbers?
Oh, absolutely. Like if you visualize the values of P312 on a graph,
Yeah.
you start to see these really, really interesting structures emerge.
No way.
Yeah, it's like looking into one of those what are they called? Kaleidoscopes where you turn it and you get these intricate patterns that appear and disappear. It's kind of like that.
That's wild.
Yeah.
So it's like you're finding this hidden message, but instead of letters, it's numbers. That makes me wonder, is there like a secret code or something, a formula that
Yeah.
we could use to decode this hidden order in P312?
Well, that's the even more amazing part. There is a formula you can use to calculate any value of P312 directly. Like you can bypass all that recursion stuff completely.
Hold on. So there's this like secret back door we can use to get the answer without all the recursive steps? What's even the point of the recursion then?
Haha, well, it's not about cheating the system or anything. Think of it this way. The formula is like, if you know the destination in advance, right? But the recursion, that's the journey. And both of those things have their own value, don't they?
Yeah, that makes sense.
The formula gives us a shortcut, sure. But the recursion, that's where the real, I don't know, the magic happens, It's the process, that journey of doing the calculations over and over. That's what reveals this intricate dance between, simplicity and complexity in these functions.
Okay, I think I'm getting it. It's like when you see a beautiful tapestry that's been hand stitched.
Yeah.
You can admire the final product, but the real like appreciation comes from understanding how each thread was woven together, the whole process that went into creating it.
Exactly. That's a great way to put it. The recursive definition, that's like the weaving process. It's building up that complexity step by step. And the fact that a formula exists for P312, it just makes it even more fascinating,
Yeah.
Because it shows you this cool interplay between order and chaos in this function. It's predictable and unpredictable at the same time. It's kind of mind-blowing when you think about it.
I know. My mind is officially blown. And you're telling me this P312 is just the tip of the iceberg.
Oh yeah, just the beginning. P312 is just one member of this whole family of functions, and each one has its own little quirks and, its own personality.
A family of functions. Okay, you've got to tell me more about P312's relatives. What other surprises do they have in store for us?
Well, there's P111. It's a much simpler one than P312, kind of like a distant cousin maybe. It's defined as f n equals 1 f n f1. And, despite its simplicity, P111, it generates the sequence that's got a really elegant pattern to it.
Oh, really? So what's so special about this P111 pattern?
It basically creates these blocks of consecutive numbers, and the
Yeah.
cool thing is that the length of each block, it's equal to the number itself.
So it's like if you imagine a staircase where each step is 1 unit higher and 1 unit wider than the one
Yeah,
before.
exactly.
Yeah.
Simple, but really elegant.
Okay, that's pretty cool. What else is in this family of functions?
Let's see, there's P123. Now, P123 is interesting. If you just look at the odd numbered values in the sequence it makes, you might think it's basically the same as P111.
Oh, so another staircase pattern.
You could say that, yeah. It's got that same block structure. But there's a twist.
There's always a twist.
Yeah.
Okay, what's the catch with P123? What makes its odd-numbered sequence different?
The lengths of those blocks, they're not just consecutive numbers. They're actually generated by this thing called a substitution system. It's basically like, imagine a set of rules that replace certain patterns with other patterns, kind of like a code.
Hold on. So we're talking about, like, simple addition and nesting, and now we have codes and substitutions thrown into the mix. This is getting pretty meta.
Right. It's like these functions, they keep revealing these layers upon layers of complexity. And we're just getting started. We haven't even touched on the T family yet.
Okay, you're killing me with the suspense now. What's so special about this T family? How are they different from these P functions we've been talking about?
Well, remember how the P family, it all revolved around addition?
Right.
Well, the T family, they swap out the addition for multiplication. And that one little change, it just opens up a whole new world of complexity, let me tell you.
It's amazing how one little tweak can totally transform these functions. It's
Right.
like if you're baking a cake and you swap out, like, I don't know, sugar for salt, you're going to get a completely different result.
Exactly. And in this case, the T family, they bring some really unexpected flavors to the table.
All right, I'm hooked. Give me a taste. What kind of unexpected flavors are we talking about with the T family? All right, I'm ready for more. Hit me with those T family functions.
So one of the really fascinating members of the T family, it's called T212.
T212. Okay, I'm all ears.
And it's defined as Fn equals 2f, n1f, n2. Now here's where things get, well, even more interesting. Unlike the P family you were talking about before, where the function, it only needs to look back at a certain number of previous values, you know?
Right, like a limited memory or something.
Exactly. But T212 is different. As n gets bigger and bigger, T212 might need information from further and further back.
Wait, so there's no limit to how far back it might need to go? That's crazy. It's like to understand what's happening today, you might need information from the beginning of time.
It's a bit like that, yeah. This unbounded look-back thing, it's a key characteristic of T212, and it leads to some truly, like, unpredictable behavior.
Wow, T212 sounds like a real wild card. This whole unbounded look-back thing has me completely captivated. It makes you wonder if there's any way to even anticipate what it's going to do next.
It's definitely unpredictable, that's for sure. But even with all that, T212 still shows some really curious patterns, you know? Like, if you look at the sequence of numbers it generates, you'll notice that all the values are powers of 2.
Interesting. So even with this unpredictable nature, there's still some underlying order there.
Exactly. It's like it's dancing on this line between chaos and order, you know? And there's more. While the sequence itself jumps around all over the place, if you look at its average growth, it's surprisingly regular. It actually increases at a rate that's related to, get the logarithm of n.
Hold on. You're blowing my mind here. You're telling me this function, with its infinite memory and unpredictable behavior, still manages to maintain some semblance of order in its growth. That's like finding a perfectly straight line drawn through a chaotic scribble.
Haha, that's a great way to put it. And that's what makes these nestedly recursive functions so captivating. They just highlight this amazing interplay between order and chaos in the computational universe. It's like they're defying our expectations at every turn.
Okay, I need a minute to process all of this. So before we move on, you mentioned something earlier about a summer school sequence. What's the story there?
Oh, right. Yeah, this is a fun one. This story takes us back to, like, 2003, the Wolfram Summer School. So picture this, a bunch of math enthusiasts all gathered together, and get this, they discovered a brand new, never-before-seen nestedly recursive function live. Can you imagine being in that room?
Seriously. Talk about being in the right place at the right time. What was this groundbreaking function?
This new function, it's called T3-1.
T3-1. Okay, what makes this one special?
So it's defined as Fn equals 3f, nf, n1. And just like that T212 we were just talking about, it also has this, like, unbounded look back. It can potentially pull information from any previous value way back in its memory.
Another one with a knack for history, huh? So did this T311, did it bring anything new to the table? Or was it basically just another T212 in disguise?
It's a great question, and you would think, right, that with this even more extensive memory, T311 would behave completely differently from T212. And here's the surprising thing. It turns out they actually share a lot of similarities in how they behave overall. It's almost like T212, even though it's simpler on the surface, it kind of already explored all the possibilities, you know?
Wow, that's pretty wild.
Yeah.
So even though they look different, T212 and T311 are essentially exploring the same computational territory, just through different paths.
Exactly. And that, I think, really speaks to the power of even these simple computational systems. You know, it's like they hold within them this vast potential for exploration. And we've only just begun to scratch the surface.
This is blowing my mind.
Uh,
Okay, so we've talked about functions with this unbounded look back, but what about those with more, well, more restrained memories? Are they out there too?
of course. And they're just as fascinating to explore. In fact, let's shift gears for a moment and talk about a different family, the S family. They have a different structure to their recursive definitions. They're defined like this: FNM, FNFNA.
S family. Okay, so a new structure, a new story to tell. Are they as complex as these T family functions with their unbounded lookbacks?
Oh, they definitely have their own unique charm, that's for sure. Let's start with the simplest one in the family, S10, or S1 for short. Now, here's the thing with S1, our usual starting point, where we assume that Fn equals 1 for n EO 0. It doesn't quite work here.
Oh, what happens? Does it just break the system?
You could say that, yeah. It actually leads to a contradiction.
A contradiction. Okay, now I'm really intrigued. So how do we even begin to make sense of a function that seems to contradict itself right from the start?
It's not as bad as it sounds. It just means we need to adjust our starting point a little bit. Instead of assuming Fn equals 1 for n AA0, we say Fn equals 1 for n A1.
So it's like we're giving the function a little nudge in the right direction, making
Little
sure
bit.
it starts off on the right foot.
Exactly.
Okay, so once we make that adjustment, what happens? Does S1 settle down and become more predictable?
Well, S1 does show some regularity, but it definitely still has its share of surprises. If we plot the values of Fn generated by S1 using our adjusted starting point, we start to see a really fascinating pattern emerge.
All right, you can't just drop a bombshell like that and not tell me more. What kind of pattern are we talking about here? Is it as mind-boggling as the T family's unbounded look back?
It's different, but just as cool. It turns out that for large values of n, the values of Fn and S1, they grow at a rate that's proportional to n divided by, get this, the golden ratio.
Wait, the golden ratio, like the same one found in art and nature? Are you serious? You're telling me it pops up in this seemingly simple recursive function, too?
Yep. It's a pretty subtle connection, but it's there. And it suggests that there's this deeper structure within S1 that we're just beginning to uncover. In fact, if we dig even deeper into the evaluation graph for S1, it actually takes on this specific form that's related to, wait for it, the Fibonacci sequence.
You've got to be kidding me. First, the golden ratio, now Fibonacci. It's like these functions are revealing these hidden connections between different areas of mathematics, like secret passageways between different rooms.
It's true. That's the beauty of exploring this computational universe. You never know what you're going to find, and it's often the most unexpected connections that are the most rewarding.
I'm speechless.
Yeah.
Okay, I think I need a moment to process all of this.
Me too.
We've gone from simple addition to unbounded lookbacks to the golden ratio and Fibonacci sequences, all in the span of, what, a few minutes?
It's a lot to take in.
It is. But before we get too carried away with these incredible patterns and connections, let's take a step back and look at the bigger picture. Well, here we are again, back for our final plunge into the depths of nestedly recursive functions. After that last part, I gotta say, my brain feels a bit like one of those functions we've been talking about, looping back on itself, but in a good way.
I know what you mean. It's amazing, isn't it? We started with these simple little rules, and look where we ended up. Unbounded lookbacks, the golden ratio, Fibonacci, who knew math could be this wild.
Seriously. It's like we've been on this incredible journey, exploring a hidden world within mathematics. But in this final part, I'm hoping we can zoom out a bit, see the bigger picture. What's it all mean?
I hear you. And the thing is, these functions, they're not just abstract mathematical curiosities. They have this rich history, and their study has really shaped how we think about computation itself.
Okay, so we're not just talking about equations on a chalkboard here.
Right.
These nestedly recursive functions have real-world significance.
Oh, absolutely. But to see it, we have to go back to the basics. When we talk about computation, we often think of computers, right?
Yeah.
Algorithms, lines of code. The tangible stuff.
Yeah, the stuff you can see and touch, the tools of the trade.
Exactly. But at its heart, computation, it's really about the transformation of information according to rules.
Okay, I can see that. Input rules, output, kind of like following a recipe.
Exactly, a recipe for information. And just like with a good recipe, the order you do things in, it really matters. Remember those evaluation graphs we talked about?
Right, the ones that show us how these functions calculate each value step by step, like a map of the function's journey.
Exactly. And those graphs, those are visual representations of a computational process. Each node is a value, each line is a calculation, and the whole graph, it shows how information flows as the function unfolds.
So are you saying that by studying these functions and their graphs, we're actually gaining insights into the fundamental nature of computation itself?
You got it. These functions, as simple as they might seem, they're like a lens, They help us study the very essence of computation. We can see what's possible, what's not, the relationship between simple rules and mind-blowing complexity. It's all right there.
Okay, that's pretty profound when you think about it. But what about real-world applications? It's great that these functions are giving us a new perspective on computation, but are they actually being used for anything practical?
That's the million-dollar question, right? And to be honest, we're still in the early stages of really understanding their full potential. But even now, nestedly recursive functions are popping up in some really interesting places.
Okay, spill the beans. Give me some examples of how these seemingly abstract functions are making their way out of the theoretical world and into the real one.
One area where they're already having a big impact is computer graphics and also fractal geometry, because they're so good at generating those intricate, self-similar patterns, the kind you see everywhere in nature.
Fractals, you mean those insanely detailed patterns that just seem to go on forever? I've always found them mesmerizing.
Exactly. And nestedly recursive functions, they're a perfect fit for generating those kinds of complex, self-replicating patterns.
So people are using these functions to create those amazing visuals you see in movies and video games, that kind of thing.
All of that. Realistic landscapes, abstract art, you name it. These functions give artists and designers a whole new set of tools. It's like, instead of brushes and paints, they're using recursion and math to create art.
That's really cool, but I'm guessing the applications don't stop there.
Oh, not even close. People are also exploring how to use them in cryptography and coding theory.
Now we're talking. Cryptography and coding theory, those are big deals. They're all about keeping our data safe and making sure information gets transmitted reliably. How do nestedly recursive functions fit into all of that?
Because they can generate such complex, unpredictable sequences, they have a lot of potential for creating new encryption algorithms and error-correcting codes.
So let me get this straight. We might be using these abstract mathematical functions to, like, protect our online banking information or make sure our emails get delivered without errors.
Exactly. And as we rely more and more on technology in our lives, having strong cryptography and reliable data transmission becomes more and more important.
You're right, we take it for granted, but without those things, our digital world would fall apart pretty quickly.
And who knows, maybe these nestedly recursive functions with their unique properties, maybe they're the key to developing new, even more secure and reliable systems.
It's wild to think about it. These seemingly simple functions, with their roots in pure math, could end up shaping the future of our digital world.
That's the amazing thing about science, isn't it? The most groundbreaking discoveries often come from the most unexpected places.
Well, I think we've reached the end of our deep dive. Any final thoughts for our listeners before we resurface?
If there's one thing I hope people take away from all of this, it's that the world is full of hidden depths. Even in the simplest things, like a few lines of math, there's this incredible potential for complexity and beauty. You just have to be willing to dive in and explore.
Beautifully said. And who knows what other wonders are out there, just waiting for us to discover them. That's all the time we have for today's deep dive. Until next time, keep those minds curious, and remember, sometimes the most fascinating journeys begin with the simplest of steps.